Dear all, thanks for having me today. My name is Alexander Gumennik, and I'm an assistant professor at Indiana University Bloomington and the director of Fibers and Additive Manufacturing Enabled Systems Laboratory, the FAMES Lab. The title of my talk is Photonic and Optoelectronic Systems in Fibers. FAMES Lab is all about functional smart fibers. First, let's ask ourselves why one would want to make fibers and textiles smart or functional. Imagine if in addition to keeping you warm and protecting from scratches, your t-shirt could, for instance, sense the level of stress that you're in, and if needed, give you a massage to help you relaxing. Or if it could store the sunlight energy collected during the day in order to warm you up during the night. Those unusual functional modalities are attainable by a set of fabrication methods that I will describe in the next couple of slides. So by our definition, smart fibers and textiles are those that perform functions beyond mechanical or thermal protection, like that of closing or point-to-point transmission of data, like that of optical communication fiber. An example of smart functionality would be a realization of 5 human senses and stimuli in fiber or textile form factor, fibers that could sense their surrounding and respond to that sensation. We want to transform a fiber from something passive like an optical fiber to something active like a microprocessor. To attain this goal, we develop a manufacturing drawing its inspiration from very large scale integration, VLSI, used in design and fabrication of modern microprocessors on a silicon wafer. And we adopt that technology for fibers. To make a microprocessor, silicon wafer surface is selectively exposed by photolithography, then is functionalized at the exposed areas by a chemical or thermal treatment, and this process results in 2D in-plane structuring of the wafer. Then the process is repeated multiple times and results in a pile of layers stacked perpendicularly to the surface of the wafer, which is an additional one dimension. Ion implantation and annealing of dopants functionalizes each device electronically, providing, in a sense, a 0D structural control of the level of the individual device. Eventually, the process results in three-dimensional structure of the microprocessor. Can we create a similar toolbox of methods for a fiber? That's the question. Our lab is striving towards such a toolbox. We call it VLSI for fibers or VLSI Phi. In VLSI for fibers, we start with 3D printing of the fiber preform to define its cross-section in 2D. It's followed by a thermal draw in order to scale the cross-sectional features to micrometric or even nanometric regime. The scaling factor of the fiber radius compared to the preform radius is tuned by ratio between the draw speed of the fiber and the feed speed of the preform. 3D printing, which is also called a freeform fabrication, results in objects of arbitrarily geometric complexity. The functional complexity of the fiber device is directly correlated to the complexity of the preform cross-section. Capabilities of the conventional, mainly manual assembly of multi-material preforms is rather limited in its architectural complexity. Thus, preforms 3D printing could potentially advance the technology and far beyond the current state of the art. Even with conventional preform fabrication techniques, a multitude of sensing and transduction modalities are attainable. Here are two examples of areas of application demonstrated. First one is functional apparel, and another one is neural interfacing. Apparel functionalities demonstrated here include physiological monitoring, shape sensing, energy generation and storage, active camouflaging. In neural interfacing, we have porous fiber scaffolds for creating an intimate contact with tissue, as well as optical, electrical, and chemical monitoring and transduction of neural signals. All that is by manual preform fabrication techniques. So imagine what can be done with 3D printing. 3D printing of fiber preforms is an emerging approach in its infancy. Our lab is making a progress on 3D printing preforms both in polymers and in silica glasses. We use a square 3D printed preform as a study system for controlling the fiber cross-section in the thermal draw. Since the fiber draw is a liquid phase process, viscosity in this process competes with the surface tension. While viscosity wants to preserve the cross-sectional geometry, the surface tension wants to defy it and reshape any cross-sectional feature into a cylinder. Cylinder is an equilibrium shape, minimizing the surface energy of the viscous thread of the liquid. Thus, if one can draw a fiber with the cross-sectional features different than cylindrical, one will be able to generalize the process to an arbitrarily shaped non-equilibrium cross-section. So roughly speaking, if one can draw a square fiber, they will also be able to draw a triangular, a star shape, or a honeycomb cross-section. To make polymeric preforms, we use extrusion-based 3D printing. Due to the nature of the printing process, the preforms have residual porosity, resulting in semi-transparent milky appearance. We improve the optical properties of the preforms by sintering them at a temperature that is very close to the glass transition of the polymer. Here you can see a polycarbonate preform. It's milky as printed, but becomes optically transparent after sintering at 165 degrees Celsius overnight, which is glass transition temperature of the polycarbonate. Surprisingly, the optical propagation loss in fibers drawn from 3D printed preforms is roughly independent of whether the preform was sintered or not, at least in the visible spectrum where the losses are dominated by the absorption of the polycarbonate itself. We think that this is due to the directional nature of the fiber drawing process. Any axial feature of the preform is elongated by 3 to 5 orders of magnitude by the draw. If the print resolution is of the order of 100 micron, it will translate into 10 centimeters to 10 meters of longitudinal distance between the scattering features for the light propagation along the fiber, which is very sparse compared to the length of the fiber section used to measure losses. Recently, we also developed a stereolithographic 3D printing of glass preforms. SLA is a technique in which liquid monomer solidifies due to the free radical polymerization initiated by interaction with a laser beam. We have mixed milled soda lime glass fiber into commercial liquid resin produced by Formlabs with volumetric infill of up to 35% and have printed preforms up to 17 centimeters long and up to 4 centimeters wide. The printed part is thermally treated to burn out the polymer and to sinter the remaining glass. In the middle panel, you see the burnt out and the sintering recipe and the morphology change between the as printed and the sintered part. We start with the resin with milled fibers sticking out and end up with a densified glass. The preform is sintered about the softening point. Thus, it's not only shrinking, but also sagging under gravity in the sintering process. Luckily, this can be accounted for in the print process in the way that we print a higher cross-section, which is wider at the top, such that when it sinters, it can sag into the desired square shape. The preform is then attached to a borosilicate tube set for a draw, as is demonstrated here on the left, and is fed up the draw furnace. In the middle is the initial drop-off at the bottom of the furnace, and on the right is the cross-section of the preform in the furnace compared to the cross-section of the resulting fiber in the inset. Comparing the preform cross-section in the furnace and the cross-section of the final fiber, we can get convinced that the cross-section is roughly preserved in the draw process. This demonstration enables us to draw silica glass fibers with non-equilibrium cross-section from 3D printed preforms. The resulting fiber is translucent, but the losses are still very high. Voids are evident in the fiber cross-section, which means that we still need to further optimize the sintering procedure. And also this particular glass has too many metal impurities, which makes it partly opaque. We should note here that the fiber draw is an axially symmetric process. A regular fiber can a regular fiber draw can result in fibers with complex cross-section, but those fibers will still be uniform along their axis. If there is a device such as a diode or a transistor in the fiber cross-section, it's the same diode or transistor spanning the whole fiber length. Since we want a true 3D architectural control over the internal structures of the fiber, we want to break this symmetry. We want to attain densely packed structures along the fiber as well, such as arrays of discrete diodes or transistors integrated into a single system. The structure of the fiber axially can be controlled by a capillary instability, tendency of liquid cylinders to break up into spheres to further minimize surface tension. The spontaneous breakup of a fluid cylinder into spheres is a phenomenon known for as long as the humanity remembers itself. It is observed daily when opening a tap of water to wash your hands or when pouring a tea into a cup. This phenomenon takes place due to a natural tendency for minimization of surface energy, which is lower for spheres than for cylinders. The way we perform the breakup is by feeding the fiber through a hot zone of a flame or a laser. For instance, if we start with a silica fiber with silicon core, as we feed the fiber into the hot zone, a short section of a core liquefies and breaks into droplets one by one in a process similar to a dripping faucet. The breakup process depends on two time scales. One is the pinch time of the droplet of the core, and another is the feed time of the breaking up period into the hot zone. Those two time scales in the steady state should be equal. While the first depends on pinching speed, which is determined by material processes, namely the viscosity of the cladding and core-clad interface energy, the other depends on the feed speed at the fiber through the flame. Thus, the breakup period is roughly proportional to the feed speed. The video here shows the breakup at various feed speeds and clearly demonstrates the dependence of the breakup wavelengths on the feed speed. The dependence of the period on the feed speed is rather sublinear than linear. This is because as the feed speed increases, the pinch location moves deeper into the flame where the viscosity of the cladding is lower, and thus the pinch speed is faster. So pinch speed is an implicit function of the feed speed, thus this sublinear dependence here. What is important is that this process is miniaturizable to submicron scale. Here is the SEM image of the spheres that were released from the fiber containing a micron pitched grating of spheres by etching the cladding in hydrofluoric acid. The resulting particles are smooth and spherical. Standard deviation in particle size is about 5%. Electron backscattering diffraction pattern measuring along the sphere meridian verifies that the sphere is made of diamond cubic silicon. But making spheres is not enough to make devices. Interestingly, experimenting with multi-core fibers, we found that the flame boundary uniquely defines the axial pinch location of the spheres. Thus, the breakup of the multiple cores of comparable sizes occurs in a spatially coherent manner. If those cores are initially separate but close enough, the spheres, which are always larger than the core due to the volume conservation, would contact into bispherical molecules. We have fabricated p-n junctions in the fiber with oppositely doped cores using this coherent capillary breakup and have measured an electrically rectifying voltage current behavior typical of diodes. Interestingly, if we would draw p and n doped silicon half cylinders in contact with one another on the preform level, the rapid diffusion of dopants in molten silicon would completely homogenize the dopants across the fiber core as it's drawn. Instead, we draw a fiber in which oppositely doped cores are separate. Then we are contacting the cores by coherent breakup, which results in fiber-embedded p-n junction molecules while avoiding dopant homogenization. To operate the device, we must contact it. A judicious choice of contacts material such that it's liquid at the draw temperature but remains solid at the breakup temperature allows keeping them intact through the breakup of the semiconductor. To demonstrate this, we have drawn a fiber where the germanium core is surrounded by two platinum electrodes. Platinum melts at 1768 degrees Celsius, so it's liquid during the draw at 2150 degrees Celsius, but remains solid during the breakup of germanium, which can be performed anywhere above softening point of the silica, which is 1650 degrees Celsius. So this gives us roughly 120 degrees of operational window for selective breakup of germanium. Now let's move to the doping control on the level of individual device. Doping control is achieved by controlling the solidification of the assembled device as they exit the hot zone. Let's take a look at what happens when the droplet is exiting the flame. Sphere cooling down on the exit of the flame experiences a thermal gradient. It is colder on the end that is distant from the flame and thus is expected to solidify laterally, starting from the colder side. If the sphere is doped with a material that is more soluble in liquid than in solid, this dopant will be repelled into the liquid as the solidification front propagates across the sphere, collecting predominantly on the hot side. This effect can be used to synthesize structured particles. Germanium and silicon is an instance of such a dopant. For instance, if we start with 50-50 silicon germanium mixture in the fiber core, after the breakup, the sphere will solidify such that the germanium is extruded into the melt as the solidification evolves, leading to an anisotropic distribution of germanium. This will result in axially oriented genus particle heterojunctions. On the left, you see the backscattered electron image of such particle in the fiber with electron diffraction spectroscopy, compositional analysis, and the graphs of content of silicon and germanium across the central line of the sphere, experimental and theoretical, and the quasi-static process assumption. And this is compared to the phase diagram of the silicon germanium system here. So now we have a combination of techniques providing 3D architectural control analogous to classical VLSI, which includes cross-sectional patterning in 2D of the fiber that consists of 3D printing of preforms and thermal draw, axial patterning in additional 1D by special coherent material selective capillary breakup of fiber cores into arrays of integrated devices, and additionally doping control plus 0D by a solidification guided segregation. Straightforward applications of VLSI Phi include, for instance, fabrication of systems of devices in the fiber, for instance, arrays of transistors contacted in parallel. This is done by a specially selective capillary breakup of a triad of P, N, and P doped cores to assemble them into trispherical molecules that are essentially back-to-back contacted diode pairs surrounded by 3 electrodes for gate, source, and drain. But I like to mention some rather non-trivial applications for tissue engineering. If you remember, we began manufacturing the fiber by 3D printing the preform. Taking a recursive approach, we can incorporate the fiber back into 3D printing feedstock. So recursive manufacturing actually has a number of pathways. One can 3D print a preform, draw it into a fiber, and use a filament as, for 3D printing objects with enhanced mechanical properties, which is shown by this pathway here. On the other hand, you can axially pattern that fiber and then use the devices that result from that patterning to print objects which incorporate arrays of devices like that, for instance, light emitting diodes. On the other hand, you can incorporate the drawn devices into bioprinting process in order to impart additional functionalities to bioprinted parts. Dashed lines here show some other possible pathways how 3D printing can integrate with fiber drawing, which haven't been explored yet but are possible. Current state-of-the-art bioprinting starts with hydrogels with premixed living cells. Those are extruded in the printing process to take a shape of a desired anatomical model. The bottleneck of this process is in the fact that while you can extrude a model that will look like a real organ, for instance, an ear, it won't function as such an organ. This is because on the micro level, it is still a soup of cells dispersed in a hydrogel. It lacks the microstructure, the vasculature, the innervation, the cartilage, the skin, and the musculature of the living tissue. We suggest fibers with a diversity of capabilities for co-extrusion with bioink that will help to solve this bottleneck. These fibers would have a microchannel system through which we can supply nutrients and building materials into bioprint that would act essentially as vasculature. It can have, those fibers can have ultrasonic sensors that would sense changes in density as the cells proliferating or dying, acting as sensory innervation system. Those fibers can have shape memory alloys that would contract or expand upon presence or absence of electric current, acting as artificial musculature and more. The picture on the right shows our first attempt to incorporate microstructured fibers into the bioprinting process using a CellLink BioX printer. So to conclude, I hope I've convinced you that VLSI-Fi enables new fiber architectures with applications in photonics, electronics, biomedical devices, tissue engineering, and beyond. I'd like to mention that the real power behind the recent progress are the graduate students of our group. Veda and Menxing working on 3D printed preforms for fibers, Camila developing device assembly by capillary breakup, and Louis and Merve developing fiber embedded bioprinting. For further and more detailed information, please refer to the paper reference here. Thank you for your attention, and I'm open to get questions either online or through my email. Thanks a lot.